Welcome back to another fun Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I'm your host for this episode, Heidi Campo, filling in for Andrew Dunkley, who is on a cruise around the world. And joining us, as always, is our beloved Professor Fred Watson, astronomer at large. How are you doing today, Fred?
Well, thank you, Heidi. We heard from Andrew a few days ago, and he was heading to far northern Norway in his global cruise. He was going to North Cape, which is it's not quite the most northerly point on the Eurasian continent, but it's very near it. And there's a globe at the end of North Cape, which sort of simulates kind of where you are on the Earth. It's a framework globe, but it's a very prominent spot for photography. I'm sure we'll see pictures of Andrew standing in front of it. I've got pictures of me standing in front of it, which I was doing in January, not on a world cruise, but one of our Arctic tours. I hope he's now vaguely on his way back home, because I don't think it's that long before he's supposed to emerge once again, bright and happy in Australia. We'll have to look out for that.
He's either going to be well rested, or he's going to need a vacation to recover from this.
Yeah, you might. That's right.
I think sometimes a trip like that, you need some time to come back down from it.
You do. And they've got some interesting things. I won't go into them, but they've got some interesting things to look forward to when they get back, which I'm sure Andrew will tell us all about when it happens. That's just a teaser for, when Andrew finally returns. Who knows when it'll be, but that's right.
Well, shall we get into our questions for today?
Yeah, sounds good.
So our first question today is from Rennie Trab from sunny West Hills, California. And Rennie says, I'm trying to understand the speed of light. What powers set it to what speed is? How different would our universe be if the speed was lower or higher?
That's an incredibly profound question from Rennie, and Rennie often does give us profound questions. What sets it to the speed it is? We don't know. We do know that the speed of light, 300,000 kilometers per second, if I remember rightly, 186,000 miles per second. That used to be the number when we did miles back in the UK. 300,000 kilometers per second, a lot easier to remember. That's the speed of light in a vacuum. It changes depending on what it's going through, but the speed of light, the maximum speed limit of the universe, 300,000 kilometers per second in a vacuum. And it's set by simply, it is what it is. It's set by the cosmic setting of fundamental quantities, because that's what it is. But it's got extraordinary significance in our present understanding of the universe. Not just because it's what lets us look back in time. When we look out into space, we're always looking back in time because of the finite speed of light. If you looked out into space 300,000 kilometers, you'd be looking back by a second, because that's how long light takes to get here. So it's, we know all about that, but it's more fundamental than that in that it doesn't change. And it's quite counterintuitive. If you imagine yourself in a spacecraft traveling along at nearly the speed of light, and you shone a torch out the front, you'd expect it to be going at nearly twice the speed of light, but it doesn't work like that. Light always travels at 300,000 kilometers per second. And in fact, that was, its origins come from work on electromagnetism done by great scientists during the 19th century. But it was Einstein who recognized its fundamental significance, and that's what allowed him to build up the theories of relativity. How different would our universe be if the speed was lower or higher? Yes, it would be. It would change the universe. Now, in an extreme situation, you might find some interest in, and I wouldn't mind betting that Rennie knows about this book, but I'll direct him to it anyway. Back in the 1950s, a very well-known physicist called George Gamow, who made some quite significant discoveries in cosmology, he wrote a couple of books where he had a fictional hero called Mr. Tompkins. Mr. Tompkins had a hairstyle very similar to mine because Gamow illustrated the book as well. But Mr. Tompkins had dreams, and those dreams basically told you about physics. The first book was about relativity. The second one was Mr. Tompkins Explores the Atom, which is about atomic physics, the quantum world. But one of the dreams that Mr. Tompkins has, but you never thought you'd be talking about this today on the show, Heidi. He dreamt that the speed of light was, I think it was something like 25 miles an hour. It was ridiculously slow. But what it meant was that all the effects of relativity, which we know about, were demonstrated at a very slow speed. This is special relativity, which is all about things moving close to the speed of light. So he illustrated a picture of somebody riding a bicycle at nearly the speed of light, 25 miles an hour, and showed the foreshortening, the fact that the bicycle seems to be squashed up because that's one of the phenomena associated with travel near the speed of light. And there are other ones as well, time travel, time dilation, your time changes. So it's a book. I still think, for all it's, it's 70 years out of date now, the relativity in it is still exactly as we understand it today, and it's worth a read. So I'd direct Rennie to that book.
That is very interesting. I'm going to be wrapping my head around that one for a while. Our next question is an audio question, and this comes from Buddy in Oregon. And I'm going to give us just a second to cue that up, and then all of our listeners will be able to hear Buddy's question as well. We're going to play that for you now.
This is Buddy from Ontario, Oregon. This is a quick one, and Fred, I guess I'll let Fred explain. Gravity and could dark energy actually be weaker and stronger nuclear forces played out at a larger scale as secondary reactions? I hope that makes sense. Thanks, guys. Love the pod.
I think Buddy might have had the same cold or fever that you had in the last episode, Heidi. Yeah, it's not the Buddy we're used to hearing. Anyway, it's an interesting question. So, could gravity and dark energy, which are forces that we understand least in the quantum world, gravity we're all familiar with, it's the one that pulls us down to the surface of the Earth. Dark energy is the property of space that we think causes the universe to expand in an accelerating manner. Could those two forces be like the strong and weak nuclear force played out on a larger scale? I like his thinking. So let me just quickly talk about the strong and weak nuclear force. We believe there are four fundamental forces of nature. And they are electromagnetism, which is the force that is allowing us to talk now and lets me see you and lets chemical reactions take place. Very important one. And then there are these two nuclear forces, the strong and weak nuclear forces, which determine the way atoms behave, basically. They are very well understood. They sound like, two angles on the same thing, but they're not. They're quite different forces. But as Rennie has sort of, sorry, I beg your pardon, as
Buddy.
Buddy, sorry, Buddy, as Buddy has indicated, they only operate on a small scale. They operate on the atomic scale. Those forces don't extend beyond. So to sort of, hypothesize that maybe gravity and dark energy we do not consider yet to be a fundamental force because we really don't understand it. But could they be manifestations of these other forces on a larger scale? And I do like his thinking. I suspect that the fundamental physicists, the people who really know about this stuff, have ruled out something like that, but I wouldn't mind betting that there is, that it's almost like an analog, one of the other, that you've got these major forces that act on enormous timescales. In fact, they're infinite. Certainly, gravity is. Gravity never fades away. It gets so small as to be unmeasurable, but never fades away. Maybe there's a nice analog between the two. I don't know enough about nuclear physics to be able to analyze it in any greater depth, but it's a question that I liked. And thank you very much, Bonnie.
Now let's take a break from the show to tell you about our sponsor, NordVPN. Now I think we'll all agree that exploring the universe is thrilling, but exploring the internet without protection, that's a black hole you don't want to fall into. Sorry. As a Space Nuts listener, we have an exclusive deal for you so you can stay protected, and that is NordVPN. It's the fastest, most secure way to browse the web. With NordVPN, you get next-level encryption, blazingly fast servers around the world, and zero tracking, so you can stream, shop, or scroll safely. It's the tool I personally trust when we're diving into the internet, and we want to give you peace of mind. I've used it overseas several times. I've used it at home. It works, and it is seamless. Head to nordvpn.com/spacenuts for an exclusive deal just for Space Nuts listeners. Big savings plus 4 months extra, absolutely free. Don't surf the cosmos unshielded. Secure your digital universe today with nordvpn.com/spacenuts, and don't forget their 30-day money-back guarantee. Go to nordvpn.com/spacenuts. Now back to the show.
3, 2, 1.
Space Nuts.
Our next question is from Casey from Colorado. Casey says, "Hey guys, just learned about ASKAP J1832-0911 and that it emits radio waves and X-rays for 2 minutes every 44 minutes. Is it true that no one knows what this is? Do you have any ideas, Fred? Love the show and hope you're both well. Thanks."
Yeah, this is a classic gobbledygook name, ASCAP J 1832 minus 90911. ASCAP is the name of the telescope that discovered this object. It's an abbreviation for the Australian Square Kilometre Array Pathfinder. It's an array of, I think, 36 dishes in Western Australia and a very radio quiet site. And the J 1832 minus 0911 is just the coordinates in the sky of this object, what we call the right ascension and declination. So it's south of the equator. That's why it's got a minus sign in front of the 9. It's a nice way of naming things by giving them their coordinates in the sky, because then you pinpoint where it is. And these coordinates are just like latitude and longitude on the Earth. So to what it is, it was discovered, as I said, by the Australian Square Kilometre Array Pathfinder, but also by X-ray observations with some work that was done using the Chandra X-ray Observatory, one of NASA's great observatories in orbit, because X-rays don't penetrate the atmosphere, at least not in the energies that we are looking at. And it turns out that this object is in a supernova remnant. So it's something that has exploded. And when you basically look at the details surrounding the object, you can see that there's a shell of gas, which is probably the shock wave caused by the supernova. We don't know when that exploded, but it was a long time ago. And so the properties that we've already heard described by Casey, this business of shining in X-rays and radio waves, exactly as he says, for 2 minutes every 44 minutes, that is still a mystery. It's thought that the source is something we call a magnetar, and a magnetar is a highly magnetic neutron star. Neutron stars being one of the possible remnants from a supernova explosion, the collapse of the core of the star into something very, very dense indeed, weighing as much as a star, but with the dimensions of a city. And that's a neutron star. Some of them are very highly magnetized. They're called magnetars, and we think they have flares on them. And some of those flares are what we think give rise to the fast radio bursts that are very much in the news as well. But this object is not like a fast radio burst because it shoots out these pulses for 2 minutes, whereas fast radio bursts are less than 1,000th of a second. 2 minutes every 44 minutes. And what that's telling you is that there's probably something orbiting something else. So there might very well be the magnetar, whose radiation is being shrouded by something else that only allows it to see to be pointed in our direction every 44 minutes. It could also be directed radiation that's squirting out from the pole of a magnetar, which means that there's a sort of lighthouse flashing effect as well. That's how pulsars work. They're neutron stars that radiate at their magnetic poles, and as they rotate, they sweep their radiation over the Earth, and we see that. So there might be that going on, plus something else that is either making the object wobble or hiding it. There are lots of people scratching their heads about this, Casey. I hope that is a reasonable explanation of what's going on. At least I think it ties in with what I've read so far about J 1832 minus 0911.
What a name.
Yeah, what a name.
0G, and I feel fine.
Space nuts.
Our very last question is another audio question, and this is from Dean from Queensland. I don't know how you pronounce that. Lots of discrepancies on pronunciation. Tomato.
Yeah.
And this is an audio question, so we'll let you guys listen to it, and we'll cue that up and play that for you now.
Fred, Heidi and Andrew. This is Dean in Redcliffe in Queensland. My question is about the image it shows us, the cosmic microwave background in space. I've assumed that this image represents the full 360 degrees of the entire sky as seen from all around the Earth, but I'm wondering if this is correct. If it shows all directions, it would be like looking at the internal surface of a sphere, which could also be projected onto the outer surface of a sphere in the same way we look at a globe of the Earth. There are many ways to project the sphere of the Earth's surface as a 2D image, but parts of it are always distorted, particularly around the edges. The 2D images of the CMB that I've seen are usually shown in an oval shape. Is the CMB image distorted around the edges? It might be, but it's hard to tell. Or is the image cropped in some way? Thanks again for the podcast.
Yeah, that's a great question. It's one I've never had before. About the shape of our depiction of the cosmic microwave background radiation. So Dean is absolutely right that is a map, effectively, a representation of the celestial sphere. And the celestial sphere is, if you imagine yourself floating in space, the sky would be all around you, and you could imagine it as a sphere. And that's basically how we imagine it from the Earth's surface, although you only see half the sphere because the rest is blocked out by the Earth itself. And what we call spherical astronomy is a really useful tool because it's what allows you to put objects in the 3 dimensions of space into their context as seen from the Earth. And the Earth's, that this depiction of the inside of a sphere being representative of the sky, as I said, is called the celestial sphere, a very useful tool. And so that's what's happened here. We see the cosmic microwave background radiation in every direction as we observe it from Earth. It covers the whole of the celestial sphere. It's faint. It's in the microwave region of the spectrum. It's mottled because of the slight variations in temperature. What we're seeing is the echo of the Big Bang there, the flash of the Big Bang which is redshifted because of the expansion of the universe since that light was emitted 13.8 billion years ago. But that's not what Dean's question's about. It's about the projection. And so it's one that's very commonly used in maps of the world. It's a projection of the sphere onto 2 dimensions, and it is called the Aitoff projection, named after a 19th century geographer, I think, called Dr. Aitoff, Aitoff. It's sometimes called an equidistant azimuthal projection because the azimuths, that's what you might call the longitude lines, are equal in distance. And Dean is right. All map projections, trying to project a sphere onto a flat piece of paper, they all have distortions. And this one does too, but they're pretty minor. And that's why it's used a lot in depictions of the whole sky, like our depiction of the cosmic microwave background radiation. So there would be some distortion around the edge, not very high level, but a little bit of distortion. If you look at an Aitoff projection of the Earth, you get an idea of the minimal amount of distortion that there are. The same would apply to the celestial sphere and the cosmic microwave background radiation. But the answer to the last part of Dean's question, no, it hasn't been cropped. That's the whole sky depicted as a 2-dimensional map. So no cropping around the edge. That's exactly what there is. It's pretty easy to find representations of the cosmic microwave background radiation where it is actually shown as a globe. Of course, we're seeing it from the inside outwards, but you can represent it as a globe as well. And if you've got animation, you can circulate the globe so you can see what it looks like on the other side. It's a lot easier to look at it on a map, like the projection that we've been talking about.
It's quite interesting. I pulled it up while you were talking because I always like having a visual. Yeah. I have the 2 monitors going on. And I'm seeing there's such a rabbit hole we can go down. I'm gonna do a little follow-up question to Dean's question. It looks like there's an axis on the cosmic microwave background, and that it lines up with our solar system, and that's kind of a point of interest and curiosity.
That's been something that's been commented on. There is, I mean. Let me just explain what that depiction is exactly. It's the microwave background. So and it's an ellipse, the Aitoff projection. The long axis of the ellipse represents the equator of our galaxy, in other words, the galactic plane. And that means that in some depictions of this, the microwave radiation from the galaxy itself hasn't been subtracted. And so you've got this sort of very bright area around the middle. But you're right, Heidi. I do remember that people thought they could see an alignment with the plane of our solar system, which is quite steeply tilted to the galactic plane. And that is a concern. I'm not sure what the resolution of that issue was. I don't think it's been a showstopper for the cosmic microwave background radiation. But I'll check up on that and try and find out whether there's any further news, whether it's just disappeared with further analysis. I do remember people talking about it. There are 3, when you look at the cosmic microwave background radiation, you'll usually come up with 3 different images. And they're only different because of the detail that they show. The first one came from Kobe, which was a spacecraft, a cosmic background explorer in the 90s. Then there was WMAP, the Wilkinson microwave anisotropy probe in the early 2000s. And then round about 2010, the Planck spacecraft, a European spacecraft, which gave us the map. It's usually coloured greenish. I don't know whether that's the one that you were looking at. That's the Planck one, which has the finest detail on it, because that was all about trying to tease out the detail in these mottles that are shown in the background radiation, which tell us about the temperature in the universe when the Big Bang was still a ball of fire.
So fascinating. I'm actually there's an image I was looking at just now that had like a cross section of each one of those images side by side. Okay. But yes, so fascinating. I mean, that's probably a whole area of expertise for someone where they just specialize in the cosmic microwave background, and that's their whole thing.
They do. Yeah, they do very serious mathematical analysis on those blobs, which tell us about conditions in the early universe. It's really quite extraordinary what you can glean from it. And the thing that always fascinates me is that when you look at that image, you're looking at the oldest thing we can ever see, the flash of the Big Bang.
Oh man, this stuff gives me chills sometimes. And that's what gets me excited about some of these like new age telescopes like James Webb. I mean, that's really it's changing the game. We're able to see deeper and further, and it's just amazing what we're able to discover now. We're really on the cusp of so many amazing things. And I think you mentioned you know, when you were young, this was in our last episode that we recorded, when you were young and hearing about some of these missions coming out and seeing these images for the first time, and to see how far that this has all come and how much further we have yet to go is just such an incredible thing to think of.
Yep. The sky's the limit, Heidi.
And maybe not even then, maybe the sky, the universe, and beyond.
Beyond, yes, that's right.
Well, Fred, this has been another wonderful Q&A episode. Thank you so much for spending time with us, enlightening us, and just giving us your knowledge and wisdom that you've spent a lifetime garnering.
It's good that it's been put to some good use, actually. I've spent my life learning facts about the universe, and it's nice to be able to talk about them with somebody like you. Thank you.
Thank you so much. Well, on that positive note, we will catch you all next time.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.